Before we delve into the description of what a white hole is, we must first understand how a black hole works, and in particular, what is the horizon of a black hole and how it behaves. On Earth, we call the horizon the distant line beyond which we can no longer see. However, if we board a ship and sail towards that line, we can cross it, we can go beyond the horizon. Crossing it does not lead to anything special. We disappear from the sight of those watching us from the shore, without any special event on the ship. Surprisingly, this is also true for the horizon of a black hole. Traveling on a spaceship, we can approach the horizon as much as we want. We can reach it, cross it. Nothing special happens. Our clocks tick at their normal rate. The distances around us continue to be normal. What happens when we enter the horizon of a black hole is that our friends no longer see us from afar. We are beyond their horizon. Like the ship vanished beyond the horizon on the sea. If, after crossing the horizon of the black hole, we try to send a beam of light back, outward, to be seen, the beam of light does not come out. It is caught inside the shell of the horizon. It no longer reaches our distant friends. Inside the horizon, the force of gravity is so strong that it even pushes light back in. So why do we often hear that clocks stop on the horizon and space tears apart? Is it wrong? No, it's not wrong. It's just the perspective of those far from the horizon. In short, near the horizon, time slows down in the sense that those who watch us from afar see us move in slow motion, but also in the sense that if we go back, more time has passed for those who stayed far away than for us. But it doesn't slow down in another sense. If we're there, we don't notice any slowdown. For us there, time passes normally. We're there. We're at the horizon's threshold. Let's cross it. The geometry of space inside the black hole is like a funnel. A very long funnel. The older the black hole is, the longer its interior is. The interior of a very old black hole can be millions of light years long. If we descend into the black hole, we are at any given moment at a point in this funnel, progressively deeper. But even if huge, the length of the funnel is not infinite. At the bottom there is still the star that collapsed onto itself to give rise to the black hole. As the diameter of the funnel narrows, that is, the cylinder becomes more curved, like a roll being rolled up tighter and tighter. The narrower the funnel, the stronger the distortion of spacetime. When this reaches the fateful Planck scale, the scale where we expect space and time to undergo quantum phenomena, we enter the region where Einstein's equations are violated by quantum phenomena. Then what happens? Then it's over. Space is compressed, time ends. We slam into a wall. If we only take Einstein's theory as valid, time ends here. But according to Carlo Rovelli, things could be different. Carlo Rovelli is an Italian theoretical physicist and writer, known for his work in loop quantum gravity and his popular science books on physics. He is a professor at the University of Aix-Marseille in France and has made important contributions to the study of black holes, the nature of time, and he made significant contributions to the development of loop quantum gravity, a theoretical framework for understanding the nature of space and time at a fundamental level. So, to understand what happens to a black hole, we must not think of it as a stationary cone with singularity at the center. We must think of it as a long tube with the star that generated it at the end. The tube lengthens and narrows and, in the future, it is crushed onto a line. The singularity is not at the center, it is beyond. This is the key to the story. And now we can move on to the topic of white holes. When a black hole enters the quantum zone, the stretching and contracting of the tube stops, and it bounces back. It starts to shrink and expand. With black holes, one can enter but not exit. With white holes, on the other hand, one can exit but not enter. Anything that has entered a black hole can cross the quantum zone thanks to the tunnel effect, pass through the white hole, and then come back out. A white hole is a future evolution of a black hole, what a black hole is destined to become. What distinguishes the exterior of a white hole from the exterior of a black hole? How can I tell the difference between a black hole and a white hole if I am outside? The answer is nothing. From the outside, a white hole is indistinguishable from a black hole. A black hole attracts, like any mass. The same goes for a white hole. There can be planets in orbit around a black hole, and the same goes for a white hole. One can fall towards a black hole, and one can fall towards a white hole. A white hole is like a reversed black hole, but that does not mean that the force of gravity becomes repulsive. By reversing the direction of time, the force of gravity does not become repulsive. As we have said from the outside, a black hole and a white hole behave in exactly the same way. They are both masses that attract with the force of gravity. Do white holes really exist? Who knows? Perhaps we may have already detected these white holes long ago without even recognizing them. Astronomers have long observed that the universe is teeming with a mysterious invisible dust that only shows up because of its gravitational effects. This is called dark matter. A portion of dark matter may be composed of billions and billions of these small, delicate white holes. Thanks for watching.